Hello everyone. Today we'll present our work on CLIDE, a zero-shot detector of AI-generated images using conditional likelihood. This is a joint work with Omer Hofman, Vainshtein, and Professor Gilboa from the Technion and Fujitsu Research of Europe. The goal of this work is to detect whether an image is real or generated, without requiring any generated images and without any retraining. Let's start with some motivation. Modern generative models can now produce highly photorealistic images that are often indistinguishable from real ones. This creates serious risks, such as misinformation, fraud, and loss of trust in visual media. Therefore, being able to reliably detect generated images is becoming a critical problem for many real-world applications. As an example, you can each take a moment to think which of the images in the bottom is real and which is AI generated. Did you get it right? To address this issue, different detection methods have been suggested. First detection methods relied on fully supervised or few-shot learning, meaning they required labeled examples of generated images. However, generative models evolved rapidly, so detectors trained on older models often fail on new ones, as shown in this matrix from the work by Epstein et al. As more and more generative models emerge, maintaining up-to-date training data becomes costly and impractical. This motivates the need for detection methods that do not depend on access to generated images. To avoid the dependency on generated examples, several zero-shot detection methods have been suggested. This means that we assume access only to real images with no generated content available and no task-specific training. Most existing zero-shot methods attempt to implicitly model the distribution of real images, often using some transformations such as compression, denoising, or reconstruction. Our method, as we will see next, explicitly models the distribution of real images. Our approach builds on clip image embeddings and on a previous method known as whitened clip. This method introduces a likelihood-based model for images using clip features. It starts by collecting a large and diverse set of real images intended to represent the full image domain. Each image is embedded using clip, and from these embeddings, the mean and covariance are estimated. A whitening transformation is then computed as the inverse square root of the covariance matrix. The whitening matrix is not unique, and in practice, this is done using PCA, which provides a specific and stable whitening solution. The whitening removes correlation and between embedding dimensions and enforces unit variance and zero mean. Additionally, a key observation is made. Clip embeddings are approximately Gaussian. In this case, the whitened embeddings are also approximately Gaussian, but now with a much simpler structure. Specifically, after whitening, the data has zero mean, unit variance in every dimension, and no correlations between dimensions. This allows us to model the embeddings using a standard multivariate Gaussian distribution. Under this model, we can compute a log likelihood score for each image embedding, which depends only on the dimensionality of embeddings and on the squared norm of the whitened vector, as shown in the equation. This score measures how typical an image is under the learned clip distribution, and it forms the basis for our zero-shot detection method. Moving on to our work, instead of modeling the full embedding space, we focus on a subspace of the representation. Empirically, we observe that these subspaces preserve Gaussian structure and have effectively lower rank covariance. This motivates modeling conditional distributions rather than the full embedding space. We can compute the conditional likelihood of a set of images from a specific domain. Rather than using the full embedding space, we restrict ourselves to this subspace. The equation shows the resulting Gaussian log likelihood in this reduced space, where the dimensionality is given by the subspace size rather than the full embedding dimension. In the plots below, we illustrate a simple case with two domains, sketches and paintings. For each domain, we estimate a whitening transform using only images from that domain. And then we compute log likelihood conditioned on each domain-specific subspace. We can see that the images tend to receive higher likelihood when evaluated under their own domain and lower likelihood under the other domain. This demonstrates that conditional likelihood captures domain-specific structure. Our goal is to use only real images to estimate the whitening transform so that generated images will appear as outliers under this model. However, there is an important challenge. CLIP embeddings do not encode only these statistics. They also contain strong semantic information, such as object category and scene type. Because of this, the global likelihood model may confuse semantic differences with real versus generated differences. For example, images of zebras and images of food naturally occupy very different regions in the embedding space, even when they are all real. This is illustrated in this figure, where the likelihood values of zebra images are lower than those of food, even if the zebra images are generated. However, the generated zebra images have lower likelihood scores than the real zebra images. We can now go over our full pipeline. First, as a pre-processing step, we extract CLIP embeddings from a set of real images we call the representative set. Next, at inference, we encode each test image with CLIP. We then find its local neighborhood among these real images in the embedding space. We use this set of local neighbors to compute a widening matrix and a conditional likelihood score. If the likelihood is low, the image is classified as generated. Moving on to results, on general natural images, we compare our method against 4 competing zero-shot baselines. The evaluation is conducted on more than 200,000 images generated by 20 different generative models. Our method outperforms most competing baselines on most individual generators and also in the overall aggregated results. Importantly, CLIDE's performance remains stable across this wide range of generative models. This demonstrates that our method generalizes well and is competitive with existing zero-shot detection approaches in the general image domain. We will now focus on specific image domains, starting with the domain of artistic images. Many existing methods experience a significant drop in performance. In contrast, our method maintains high detection accuracy. We also evaluate our method on a more specialized domain of damaged car images. This domain is motivated by the risk of insurance fraud, where generated images could be used to fabricate car accidents. Once again, the performance of other methods degrades substantially, while our approach remains reliable. This highlights the domain-adaptive nature of our conditional likelihood method. Finally, we test on invoice images, which are far from natural photographic data. Despite this shift in domain, our method continues to perform well, while alternative approaches struggle. This demonstrates that the method can adapt across very different visual domains. We also identified a recurring failure in existing zero-shot detection methods. The distribution of real and generated images overlaps significantly and, more importantly, flip sides depending on the generative model. In contrast, our method produces strong separation and consistent ordering between real and generated images across models. This consistency is important for reliable detection in practice. To conclude, we show that conditional likelihood can be used to detect AI-generated images in a zero-shot setting. Our method is domain-adaptive, requires only real images for calibration, and does not rely on access to any generated data. It outperforms existing state-of-the-art zero-shot methods in both a general image domain and in specific domains. It also exhibits consistent separation behavior across domains and generators. We believe this makes it a promising direction for robust and practical generated image detection. Thank you for watching, and I hope you enjoyed this talk. Please feel free to contact me and ask any questions you have.